Yeah, sweet. Okay, so it says to draw an angle of 76.425 degrees. Draw it first, and then we're going to convert that to degrees, minutes, seconds. So 76, that's going to be what type of angle? Acute, right? So as long, and if you want to like think of it, a 90-degree angle, there's kind of horizontal. 90 would be straight up, so maybe somewhere in there. That's kind of a good way to think about it. And then we'll put a little arc in there. You don't need to put arrows on the arc. Let's give our angle a name. What do you want to name it? A? Alpha? Alpha? Okay. So you can call that alpha. And then we'll come up here and we'll just say then alpha equals 76.425 and then degrees. That's kind of a nice way to do it. So it's both the name of the angle and the size of the angle. Now, when we drew it like that, because it's, again, planar geometry, that angle can be pretty much oriented anywhere. You know, that little arc that we drew kind of locks those rays the same distance from each other. So however you draw it, that's the exact same angle. That's not going to be the case when we start looking at coordinate geometry. But anyway, there's the angle. I'll put them right there. Okay, sounds good. But now we want to convert it to degrees, minutes, seconds. So what we're going to do is pretty much what we did in the warm-up when we converted hours to hours, minutes, seconds, because we learned yesterday these little conversions right here, just like with time, 1 degree is 60 minutes, so degrees act like hours, and 1 minute is 60 seconds. So we can use the exact same conversion factors. So when I talk about conversion factors, these are fractions that are equivalent to 1. Conversion, let me try that again. I'm talking while I'm writing. Conversion factors. These are equivalent to 1. They're not equal to 1, but they're equivalent to 1. So you could say 1 degree is equal to 60 minutes, or you could flip conversion factors. 60 minutes is equal to 1 degree. So when you're doing your stoichiometric conversions or dimensional analysis, as long as you're multiplying by a fraction that's equivalent to 1, and you have your desired units appearing and the ones you don't dividing out from high to low, you know you're doing it right. So it's kind of a fail-proof way to do a problem. So those are both the same. You can flip them as needed. And then we also have 1 minute is 60 seconds, or you can flip that 60 seconds is 1 minute. Okay, so let's go ahead and convert it. 76 full degrees and then 0.425 of another. That's not quite a half of another degree. So when we convert that to DMS, we know it's going to be 76 full degrees. So remember what we just did in the warm-up is we took the fractional part, 0.425, and we multiplied it by 60. Okay, so when we quiz tomorrow, I do want to see these computations times 60. And again, the reason it works is 0.425 is degrees over 1. And then times, that's going to be 60 minutes over 1 degree. That uses that conversion factor right here, okay? And what happens with your degree bubbles? They divide out, okay? And you're left with minutes, so you know you're doing it right. That's why stoichiometry is so useful. So really, all we have to do now is punch that number in. So let me go ahead and do that. I'll come over here, 60 times 0.425. It should be less than 30. 25.5. So I'll write it down right here, 25.5. But now the 0.5, that's another half of a minute. Well, we know how many seconds a half a minute is, right? It's 30. So you can write that down, or you can do this again, 0.5 times 60. And again, the reason it works is that's 0.5 minutes over 1, and that's 60 seconds over 1 minute, and now your minutes divide out. So if you did that in your calculator, you will get 30, and it terminates. All right, so now we can write our answer. We could say that 76.425 decimal degrees is equivalent to 76 degrees. And we're not going to say plus. We don't really put a plus sign. And we talked about GPS format yesterday. You just write it next to it. The units almost become the separation there. 76 full degrees, 25 full minutes, and then 30 full seconds, okay? And there it is. So you can read it as 76, 25, 30. And I did pull up Google Maps yesterday, and on my phone, it's kind of a new phone, it automatically, it's kind of interesting. It gave the latitude and longitude coordinates down the bottom as decimals, and I didn't even do anything different. I just clicked on it, and it converted them it gave me the GPS coordinates in degrees, minutes, seconds. So that was kind of interesting. I haven't seen the coordinates given as decimal degrees before, but when I touched it, it turned to degree, minutes, seconds, which is almost as easy as what your calculator can do. And I'll show you what I mean by that here in just a second. So first of all, are there any questions on the computations? Pretty easy, right? Pretty darn easy. Now, because you know how to do the computations, right, we're learning why things work and not just how to do them, your calculator can actually do it for you. So this would be a real quick, fast way moving forward so you don't have to go times 60 times 60. But on the quiz tomorrow, I do want to see times 60 times 60. So you can actually come over here and clear your home screen, type in 76.425. And your calculator has an angle menu. It's the second command under the apps button. So if you hit second apps, apps is to the right of math. It's column 2, row 3. Yeah. Notice you have some options there. There's the degree symbol in number 1. You have the minute symbol in number 2. You have the letter R, lowercase, in number 3. And look at number 4. That little caret that's pointing to the right, or that arrow that's pointing to the right, you know what that means because you've used that so many times when you're converting decimals back to fractions, right? Math enter, enter. Everyone's used the math enter, enter button. That means convert to DMS. So go ahead and select number 4, and then just hit enter. And then boom, there it is. It gives you 76 degrees, 25 minutes, 30 seconds. Okay? So I want to make sure you know how to do it manually. I say manually, but we're still using the calculator over here to do the multiplication for us. But you're showing the process, times 60 times 60. So almost identical to what we did in the warm-up, except instead of hours, we have degrees. Comments, questions, quiz, scopes, concerns that are not about the national championship game? Wow. Okay. So here we go. New Braunfels, Texas. New Braunfels, Texas. Anyone ever been there? Yeah, sadly. Yeah, we're here right now, actually. If you looked up the official GPS coordinates of New Braunfels, Texas, on the, I guess, the Wikipedia page, you would see that it lies at 294210 north. That's kind of how we read that. 294210 north by 98727 west. Now notice those are GPS coordinates. So I don't know exactly. That's a pinpoint. That is a single spot somewhere in town. And I don't know exactly where that is. If I had to guess, I would say probably downtown at the plaza, right? That would be a good central place to demark New Braunfels, Texas, right? Or it might be at the courthouse, or it might be in the living room at the mayor's house. I don't know, okay? I think it is somewhere on the plaza. People have looked it up before, and it's kind of like by the NBU building. But we want to convert those to degrees, back to decimal degrees. As I told you yesterday, my phone gave me decimal coordinates for latitude and longitude, and then I touched it and it converted it to these. So we're basically going back the other way. I want to convert the parts of full degrees. Let's do the latitude first. I want to do the 42 minutes and the 10 seconds. I want to convert those back to degrees, right? Now, we did going from decimal degrees to degrees, minutes, seconds in 2 steps, right? Convert the decimal, write down the whole number, convert the decimal, write down the whole number. But when we go backwards, we're going to do it in a single step, all right? So here's what I would want to see. We have 29 full degrees already, plus. Now I need to take those 42 minutes and convert that part back to degrees. So I'm going to multiply by a scale factor or a unit conversion factor that's equivalent to 1. All right? So I need to convert it back to degrees. So the degrees needs to be in the numerator, and I want the minutes to divide out. So since the 42 minutes is in the top, I would need my minutes to be in the denominator on the other factor to divide out. So what is the conversion factor? Is it 1 over 60 or 60 over 1? 1 degree is 60 minutes. Yeah. And it makes sense what we're doing. We're essentially dividing by 60, correct? In the previous problem, we multiplied by 60. Now, that is going to give you degrees. And that'll tell you how many degrees 42 minutes is. But we can immediately add on the other part. I have 10 seconds. And so just like trying to figure out what fraction of an hour 10 seconds is, we're trying to figure out what fraction of a degree 10 seconds is. I need to convert that. So let's multiply by a fraction equivalent to 1. So I want seconds to divide out, so I need to put it in the bottom. Now, you might need to do two conversions here, right? If I want to go from seconds to minutes, that would be 1 minute is 60 seconds. Now notice the seconds divide out. But I'm still left with minutes, and I want to convert that to degrees. So now I'll multiply again by a conversion factor. 1 degree is 60 minutes. Okay, so notice what we're doing for the seconds. We're dividing by 60 not once, but twice. And if you notice, then your minutes divide out, and you're left with degrees. So as long as your units are dividing out from high to low, you're doing it correctly, as long as those conversion factors are equivalent to 1. All right, so that's what it looks like. Now, how many people know how many seconds are in an hour? Anyone know that? A lot? Yeah. If you know how many seconds are in an hour, you could go straight from 10 seconds. You can multiply by 1 degree over, 3,600 seconds. And you could do it in a single conversion factor. How did I get 3,600? Well, what's 60 times 60? 3,600, yeah. So I don't care how you do it, but tomorrow on the quiz, I do want to see this stoichiometry. So 29 plus 42 divided by 60 plus 10 divided by 60 twice. All right, so I'm going to go ahead and type this one into my calculator, and I'm going to do it in one fell swoop, okay? I'm not going to do it in sequences anymore. I'm just going to type it in as 29, and now plus 42 divided by 60, plus 10 divided by either 3,600, or you say divided by 60 divided by 60. Notice that's very important. If you put divided by 60 times 60, because there's two 60s in the bottom, it's going to multiply by that second 60. So you put divided by 60, and then you divide by 60 again. Okay, and there you go. You get then 29.70, and then we report 3 decimals. So you can put 702 degrees or 29.703 degrees. I'll take either one of those. Does it? Oh, yeah. We'll get to that. Yeah, it does give you the answer. You're right. And luckily we get the same answer as what's in the text over there. So that's so New Braunfels lies at 29.702 or 703 degrees north latitude. Now, which one of those is actually more accurate? The degrees, minutes, seconds, or the decimal degrees? Well, kind of. They're very, very close to each other. I mean, if you went to one coordinate in degrees, minutes, seconds versus the one in decimals, you'd be standing probably on the other guy's foot. But the one that's in degrees, minutes, seconds is actually more accurate because it's 2942.10, where 10 is a terminating number, right? And what did we do with decimals? It's 29.70277777 repeating. So anytime you have a decimal and you're truncating or rounding, it's no longer exact or as nice. So the other answer is a little bit better. So go ahead and do the same thing with 98.727 on your own and make sure that you show the work. I'll show the work over here, what I would expect to see on tomorrow's test or quiz, I should say, little test. All right, so you can write it out exactly as we did on the latitude coordinate with the units and divide them out. That's good affirmation to yourself that you did it correctly. But at the very, very, very least, what I would expect to see on tomorrow's quiz is what I have written there. 98 degrees with units plus the minutes, 7 divided by 60 degrees, plus the seconds, 27 divided by 3,600 degrees. That would be the least you can write and get away with full credit, okay? And then you just type that into your calculator, as I did there on the left, in one step, right? 98 plus 7 divided by 60 plus 27 divided by 3,600, and you get 98.124, and that's the same answer when you round or truncate. So that's the longitudinal coordinate of New Braunfels, Texas. And now, if you would like, you may get your phone out and you may text your results to your parents and just say, hey, Mom or Dad, did you know that New Braunfels GPS coordinates in decimal degrees are 29.702 by 98.124. And people have done that in the past. Here's one that was from 5 years ago. And then the mom goes, okay. And so she followed up. I just wanted to tell you because I love you. And then I love you too. See? Look at that. Right? And then this one over here. This one, there's graphics on this one. This was from 2011, even longer ago. Okay. Another okay response. But this one was just okay. And I just thought you should know because I care about you. And then Mom didn't follow up. Like, yeah, whatever. So anyway, if you want to do that, it's good information. It's good information for your parents to know. Now, once we do it like this, you can always convert it like this, right? But your calculator might be able to convert it on its own. So if we do that, it's going to be a little bit different. Let's go ahead and confirm the 98,727. If you're going to have your calculator convert from degrees, minutes, seconds back to decimal degrees for you, you have to type your answer into the calculator as 98 degrees, 7 minutes, 27 seconds. So let's go ahead and do that. I'll show you from the home screen. We'll flush. We're going to get 98 degrees. Now, remember where the degree button or the degree bubble was found? Second apps, right? And it's number 1. Boom. So that's 98 degrees. You don't put plus. You just type in the 7. And then go back to your angle menu. Second apps, it's number 2. It's the single dash. There it is. And now you just type in 27 and you go for the double dash. So you go back to that angle menu, second apps, and where's the double dash? It's not there, right? And if you tried putting 2 single dashes, right, number 2, it doesn't work. So, where in the heck, how can we do this? Where is the double dash? They don't have it under the angle menu, but it is somewhere. There you go. If you look at the alphanumeric feature on the plus sign, which is really the quotation mark, it acts as a double dash, okay, or double hat tick mark. So there it is, 98,727. And now all you got to do is just hit enter. You just hit enter, and it converts it for you, 98.124. So that's kind of nice. All right, so after tomorrow's quiz, unless I specifically ask you to show the computations after tomorrow's quiz, if you need to convert back and forth from one to the other, you can let the calculator do it for you. Okay? Sweet. Now, real quickly, let's just talk about how we get those measurements. Okay? It's kind of interesting, and I'll do it very, very quickly here. There's Earth. You see that? It's round. Right? It is flat because it's depicted on a two-dimensional surface, but the actual Earth itself is not flat. Sorry, guys. So here's the literal center of the Earth, right? Don't go there. It's kind of hot. All right. So we have this line here called the equator, right? Oh, am I? Oh, good. Good for me. Yeah. If you were to draw a line straight across from the center of the Earth to the equator, you can measure then an angle right here. Call it theta. That's going to end up being your latitude coordinate. Latitude coordinate. And we have north, which is if you rotate up into the northern hemisphere, and you can also rotate down into the southern hemisphere. Okay, we'll call that also maybe another alpha. So that's how you get your latitudinal line. It'll intersect the Earth at some point. So if it intersects right there, you are now at this latitude. You might have heard like the 42nd latitude. The 42nd latitude line would be if you went up at an angle of 42 degrees and intersect the Earth and then go all the way around. That's the 42th latitudinal line north, and then you can also do the 42th latitudinal line down. And then it works the same, well, not the same way, but very similarly here for the longitudinal. Now, the latitudinal lines vary in size. It's like slicing a tomato for a hamburger, right? If you slice the tomato near the middle, the slice is bigger. If you slice the tomato near the end, the slice is smaller. But the longitudinal lines are great circles. And what does a great circle mean? Not only does it mean that it's a fantastic circle, but it means that they're all the same size. So they would run through the North Pole and the South Pole. So there's one. If you basically imagine taking one ring that runs from the North Pole to South Pole and you rotate it around, okay, you're going to get a bunch of other lines that are exactly the same. And so we have a zero. This one here, you all know what the zero longitudinal line is? It's not the equator, but the prime meridian. Yeah. And so from the prime meridian, you could actually then rotate from there however many degrees east. Oops. From our perspective. Dang it. I am messing up, dude. Nope, that's it. That's not. Did I delete it?
No.
No. Okay. This would be, you would rotate a certain amount, between 0 and 180 east, or you can rotate that amount west. And basically, let's say we rotate a certain amount this way, that is going to intersect that longitudinal line right there, and that would be the coordinate. So that's how you navigate through an elliptical space like that with GPS coordinates. Okay, pretty nifty, pretty nifty. Any other comments or questions about that? Anyone figure out where that actually is? Anyone Google it? Do we have time for that? I don't know if we have time for that. I don't know if we have time for that. Mrs. Lincoln's already way ahead of us. I kind of drift. Okay, so let's go ahead now and kind of get off just the regular plane and start standardizing our angles on the coordinate plane, coordinate geometry. So here's the definition. We say that an angle that is in standard position has what we call the initial ray on the positive x-axis, okay? The terminal ray, which is the other ray, terminal means end, right, like the bus terminal. The terminal ray may land anywhere. So let me go ahead and show you what I mean. Let's draw ourselves an x and y axis. There's the y-axis. There's our beloved x-axis. All right, so now what we're going to do is we're going to say we have an angle in standard position whose tail, whose fixed end is the origin, and that goes out in the positive x direction. This is what we call the initial ray. Initial means beginning, right? Initial ray. The terminal ray, it can land anywhere within the four quadrants. So if we rotate this direction, which would be what, clockwise or counterclockwise? That's counterclockwise, CCW. We are going to designate that as a positive direction, okay? A positive direction. So you can rotate all the way around between 0 or 360 and stop. Wherever you stop, though, you're going to get that other ray, which is called the terminal ray. And that angle there, theta, I'll write it there, would be now a positive acute angle in quadrant 1. It has an initial ray, which is always, always, always on the positive x-axis, and the terminal ray can land anywhere. All right, so we designate the counterclockwise position the positive, because that gets us to rotate through quadrant 1 first. And notice if I keep rotating, I get my quadrants labeled 1, 2, 3, 4. So if you've ever wondered why the quadrants are labeled like that, it's because the way that we designate a positive angle. It rotates in sequential order. Now, in planar geometry, you don't have negative angles, right? It doesn't mean anything to have a negative angle inside of a triangle, does it? But guess what? We can have negative angles now. I can start on the positive x-axis, which is my initial ray, and I can rotate around over here. Let's rotate all the way around over there. Let's keep going. We'll rotate into quadrant 2, and then I'll stop. There's my terminal ray. Here's my initial ray. Let's call that angle alpha. If you rotate in the clockwise direction, that's going to be designated as a negative angle. So what would be an approximation then for alpha? Can y'all tell me? Alpha then could plausibly be what? Well, let's see, it's going to be negative. Why is that angle going to be negative? Clockwise direction. Right, I'm passing through the quadrants in reverse order. Let's count, let's see how far we rotate. We rotate 90 degrees to get straight down, then another 90 degrees to get straight across, plus about another 45. So 135? Well, it's got to be like 180, right? Negative 225 is a really good approximation if you think that we go 45 more degrees. So wow, negative 225 is kind of a blow me away angle for y'all at this moment because of two reasons, right? First of all, it's a negative angle, which you never had in geometry, and it's an angle that's bigger than 180, which you never had in geometry, right? But we can talk about a negative called a reflex angle if it's bigger than 180. Now, no problem, okay? It's just designating how far we rotate around the coordinate plane. Could we have an angle that's bigger than 360? Yeah. Yeah, let's do that. Let's start on the initial ray, and let's rotate all the way around to 360. Plus, let's then go up to that terminal ray, which you could say is another 45. Let's call that one beta. Is that going to be a positive or a negative angle? If I start on the positive x-axis and rotate counterclockwise, it's going to be a positive angle. And let's see about how big it's going to be. I go all the way around. A full rotation is 360 plus about another 45. 405. Wow, 405. So beta is approximately 405 degrees. Okay? Everyone okay with that? So now this is in standard position. No longer are we just going to draw angles like we did on example 1, where it could just be anywhere, right? That angle, as long as you know, the the rotational measure between the rays is the same, it's the same angle. That's not the case anymore. Okay, a degree of 76.425 would terminate in quadrant 1. Okay. Blah, blah, blah. So let's look at some of these angles here. Here's this angle in standard position. Now notice we're only highlighting the initial ray. You see that? Or the terminal ray? The reason we don't highlight the initial ray as well is because by default the initial ray never moves. It's always along the positive x-axis. So you don't even have to draw that anymore. The x-axis itself forms that ray. Now notice the arrow is kind of nice to show. Although you don't have to show it, the arrow is nice to show because it shows you the direction. So now our angles are really vectors. They have a magnitude and a direction. It shows that we're rotating in the positive direction. Here's one kind of like what we did, right? Negative 225. It's clockwise, so it's negative. It terminates in quadrant 2. Here is one kind of like exactly what we did. We went all the way around to 360 plus another 45. And then here's one that makes me dizzy, right? Is this one going to be positive or negative? It's going to be positive, and let's see about how big it is. We rotate all the way around to 360 plus another 180. So if you want to keep track, there's 360 plus another 180, and then plus another 45-ish. So that ends up being 585, something like that. Positive 585 degrees. That's pretty hot, right? No, what actually would be hot if it was in Fahrenheit. But we're not saying degrees Fahrenheit, degrees Celsius. We're just saying degrees, right? Degrees. Okay, cool. So here's what we're doing now. Example 3, draw the following angles in standard position. It says to show the arc between the initial and terminal ray. Will do. Theta equals 190. I'll do this one with you, 190. So draw your x and y axis first. That's the first step. Are we going to rotate clockwise or counterclockwise? Counterclockwise. So 190. We're going to go all the way to 180 plus about 10 degrees more. Boom. There it is. That's all you have to do. If you want, you can label that theta right above the arc. 190 degrees. I'm not going to take out any kind of protractor and measure to see how accurate you are. Essentially, if it's reasonable, you got it terminating in the right quadrant, you're going to be in good shape. Notice again, I did not even draw my initial ray, but I showed my arc starting on the positive x-axis. So that's really about all you need to do. All right, letter B. You do. Letter B. It's beta. B is beta. It's kind of helpful to know your angles that land on the quadrants, right? 90 degrees is a quarter rotation, 180, 270 would be 3/4 of a rotation, and 360. That's kind of helpful. 0, 90, 180, 270, 360. All right, a real simple multiple choice question on a test is, in which quadrant does beta terminate in? Quadrant 1? Yeah, I agree. It's a negative angle, so it's going to rotate clockwise. Here's 90 degrees. There's 180 degrees. There's 270 degrees. And then we go an additional 6 degrees, which is a little bit more. So I'll call that beta right there. And now it ties it into what's up above. Yeah, pretty easy. Terminates in quadrant 1. Letter C. That letter is what? We talked about it yesterday? It's theta, but it's turned vertically. It's actually a vertical tangent. It's phi. Yeah, it's phi. All right, go ahead and draw that. You might be done. What quadrant does phi terminate in? 3. Yeah, it's negative. So we start on the positive x-axis. We rotate clockwise. There's negative 90, and we go 1 more degree, just a hair more. And then you label the arc phi. There you go. Terminates in quadrant 3. All right, go ahead and do this one, 629. I'll let you do that one on your own. Might have to do some stack subtraction off to the side. Or you have your calculator, I guess. It terminates in quadrant? Actually 3, yeah. So we're rotating clockwise because it's a positive angle. 629 is bigger than 360. So you can go off to the side or with the calculator and do 629 minus 360. That subtracts the full rotation, and it tells you what's left over, 269 degrees. So when you're drawing it, you draw your arc, you say, okay, I got to go a full rotation, so that's all the way around, that's 360, plus an extra 269. So remember, 3/4 of the way around is 270. So we're going, there's 90, there's 180, and I'm stopping 1 degree short of 270. So that's in quadrant 3. So that angle is 1 degree off of the negative y-axis. What did you notice about angle C? How far was it from the y-axis angle measure? 1 degree, right? these two angles right here, they terminate at the same place, right? That's kind of interesting. Does that mean they're the same angle? No, they're not. 629 is a much bigger angle than negative 91, but they stop at the same place. They share a terminal ray. They have a name. All right, 1822, what a great year. Now, 1822 is bigger than 360, so it's more than one rotation. It's bigger than 720, so it's probably bigger than two rotations. What are three rotations? Gosh, I don't know. So the way you could do this one, if you have your calculator, let's go to the calculator, is you could just type in 1822, and then you can subtract 360 and hit enter, and that's 1462. You could subtract 360 again from that answer and hit enter, and you get 1102. Now here's what's cool about your calculator. If you do the same thing twice in a row, minus 360, minus 360, it remembers what you're doing. So after that, all you have to do is keep hitting enter. Okay, whatever you want to do, you can keep doing minus 360. And that's 382. That's still bigger than a full rotation, so there's 22. So what that means is I have to rotate around many times. I forgot how many times it was. Did y'all? 5? 1, 2, 3, 4, 5 full turns, and then 22 degrees, which is going to be somewhere right in here. Now, ultimately, we're not going to be drawing, bless you, all of those arcs making the complete circle, because you can see it starts to look like that MASH game you played earlier in your life. And it also can give you vertigo because it looks like a spiral. And it's also cluttering up the graph, right? So what we're primarily interested in is, okay, it makes 5 full revolutions and then an additional 22. So that terminates in quadrant 1. Now, instead of subtracting 360 over and over and over again, which certainly works, is there a quicker, faster, more efficient way to figure out? We really were after that 22, that residual amount. Is there a faster way to do that? Sure. Okay, Darryl, how? Don't know. Yeah, very good. You could divide by 360. Take that angle, 1822, and divide by 360. Again, we're doing stoichiometry here. What does that number give us, Stacy, when we divide by 360? Yes, because there's 360 degrees in one rotation, it tells you when you divide by 360, it tells you how many times you're going around. You're going around 5 full times, which gets you back to the same place, plus an additional 0.06 of a time. We really just want to know what that 0.06 is, right? So here's what you could do. If that's 5 point something, just say minus 5 and hit enter. You don't want to type in 0.0611 because then you're not using the full value. But if you subtract the integer amount, 5, now the calculator is still storing the decimal amount. How could I then figure out what that is in degrees? Not divide by 360. Yeah, because that's the fraction of a rotation. Now I'd have to remultiply by 360, and that gives you 22. Okay? So that's an easier way to do it without having to keep subtracting 360. Divide by 360, cancel out the integer amount, and then remultiply by the same number, 360. So that tells you in 5 full rounds, and then an additional 22 degrees. All right, last one of the day. Go ahead and figure out what quadrant this one terminates in. Negative 57631. Ooh, doggy. All right, you go, however you want to do it with the calculator. You definitely don't want to have to draw all those arcs this time. You can just tell me how many. Yeah, it's quite a few. Oh, I'm not sure. I haven't worked in a while. Now, here's one way to do it. Some of y'all are found it the efficient way. I typed in negative 57631. Because it's a negative angle, that means we're going what? Clockwise or counterclockwise? Clockwise. If you want to then start getting back to something between 0 and 360, because it's a negative angle, you have to add 360 instead of subtract it. So plus 360 plus 360, and now if I do it, since I've done it twice, I can just keep hitting enter right here. And notice I'm slowly getting back to something between 0 and 360. But that's going to take a while, right? But if you enjoy having fun, this could be something that you might want to do. It's going to take you quite a few times, but you could get there. So the efficient way, again, is negative 57631 divided by 360, the number of degrees, in a full rotation. Now, that's negative 160 degrees. So I would have had to hit that button 161 times. To get rid of the negative 160, because it's the 0.086 we're after, because it's a negative number, you have to add the 160 back, okay? And now I have negative 0.086. I then turn around and multiply just the fractional part by the exact same number we divided by, 360. And it tells me negative 31. So I like what some of y'all did here to show the negative 160. You went like this, and you just kind of, and then negative 31 is going to be down here. Okay? So it does live in the fourth quadrant. Very good. Huh? No, you don't have to do that. You could just do that right there. Okay? But just be ready to tell me that it makes 160 full rotations. Okay? All right. We're done for the day. Quiz tomorrow. Make sure you know how to do that. All right. Quiz tomorrow over anything we've done in the last 2 days.